Hello, welcome to another module in this massive open online course. So, we are looking at discrete time Markov chains and the transition probabilities, how to characterize the discrete time Markov chain and so on. We have seen in particular the one step transition probabilities. Now, let us ask the question, how to characterize the n step transition probabilities, right. So, we want to look at the n step transition the n step transition probabilities for this DTMC. That is, we want to ask the question, or let us put it this way, let us say the m step transition probabilities, right, m step transition probabilities, or we want to ask the question what probability x n plus m equal to S j given x n equal to S I, that is, we are taking m steps, right. Previously we were setting one step, now we want to look at what is the m step transition probability. To begin with, we can set m equal to 2. Okay. So, we can ask the question what is the 2 step transition what is this 2 step transition probability. Okay. So, remember we have the one step transition probability matrix, that is, we have the matrix probability x n plus 1 equal to S j given x n equal to S I, right. So, we have P I j equals to probability x n plus 1 equal to S j given x n equal to S I, and we put together in this matrix P. This is essentially our transition probability the transition probability matrix, and by default this means the one step transition probability matrix, that is what we say. We do not mention it explicitly. Whenever we say the transition probability matrix, by default it means the one step transition probability matrix. Okay. So, I think that is something that you would like to keep in mind. There is not any arbitrary number of steps, but this is the one step transition probability from which we can derive the n step transition probability matrix, as we are going to see. So, consider now P multiplied by P, that is equal to P square. Now, if we look at what is the I comma jth element of this matrix P square and ask that interesting question, what is the I comma jth element of P square? Remember, this is each P is an n cross n matrix, n equals the number of states. Now, what is the ijth element of P square? So, this is essentially you sum over k equal to 1 to n P I k times P k j, P I k times P k j summation k equal to 1 to n. This is the standard expression for the matrix product. But now, if you look at this, this is interestingly, because using the time homogeneity property, what happens to this is this, you can write it as the product of these two one step transition probabilities P, you can write it as P x n plus 1 equals k or S k given xn equal to Si, that is this, times the probability. Now you can write it as xn pkj, you can write it as xn plus 2 equal to xn plus 2 equal to j given xn plus 1 or xn plus 2 equal to sj given xn plus 1 equal to s, xn plus 1 equal to sk, because remember we are using here that the time homogeneity property, that is xn to xn plus 1, xn plus 1 to xn plus 2, these probabilities are the same, the transition probabilities are the same, right. So, that is essentially the time homogeneity property. So, this follows from the so what we are using here is the time homogeneity property. We are following the time homogeneity property, and so therefore, now this can be written as, and now you can see this is essentially, if you look at this, right, if you look at this, this describes going from xn to the state xn plus 1 to the state xn plus 2. So, we have xn in state Si, xn plus 2 in state Sj, and xn plus 1. So, through Sk one is going to Sj, and we are computing this probability, that is probability of this transition and summing over all Sk. So, essentially what we are doing is we are doing the probability, if you look at it a little philosophically, we are doing the probability Si to Sk to Sj, that is, if you have to go from Si to Sj in 2 steps, you have to pass through some intermediate step Sk, and now you are taking the sum of these probabilities over all k equal to 1 to n, and this is nothing but, now each of these is disjoint, these are disjoint events, or these are mutually exclusive and exhaustive. So, if you look at in terms of probability theory, these are mutually exclusive plus mutually exclusive in the sense that if you go from Si to Sj through S1, and if you go through from Si to Sj to S2, these two events are mutually exclusive, their intersection is 0, and they are exhaustive because you have to go from Si to Sj through at least one intermediate step in between. So, they encompass the complete sample space. So, therefore, one can use the total probability rule to now find the probability of going from Si to Sj. This is basically falls out from the total probability rule. So, using now the total probability rule, this essentially gives you the probability of going from Si to Sj in 2 steps. In 2 steps, which we are writing as the probability xn plus 2 equal to Sj given xn equal to Si. So, this essentially follows from the total probability rule. If you are not familiar with this, I urge you once again to revise your, this follows from the total probability rule. So, again please look at your, refresh your concepts, knowledge of the principles of probability. So, we have this total probability rule which states that essentially if you have what is the total probability rule? I think it is interesting to just mention it briefly. You can write probability of any event A as the summation of probability A intersection B I, where I equal to 1 to n, where B I, the only property that the B I must satisfy is that B I are mutually exclusive and they are exhaustive. This implies that B I intersection B j equal to phi for any I j, and the union B I over all B I, this is equal to S, where S is basically the sample space. That is basically, if you look at any two events, these any two sets, that is these two events should be any two events B I B j, these should be mutually exclusive and exhaustive. Exhaustive in the sense their union must span the sample space, and that is exactly what we have over here. If you look at the transition, two-step transition from x I to x j, it must go through any intermediate stage or step, any intermediate state S k, and if you look at all such transitions, these are mutually exclusive, because if it is going through any particular state S 1, or if it is going to any particular state S k, it means that it is not going through another particular state S k prime. So, these are mutually exclusive, and further exhaustive, because it must go through at least one of these states S 1, S 2 up to S n in between at time instant n plus 1. All right. So, it is very straightforward to deduce this thing, and naturally therefore, you can see that the ijth and the conclusion of this entire simple derivation is that the ijth element of p square is the two-step transition probability of going from x n in state S I to x n plus 1, x n plus 2, it being in state S j. That is the idea. So, idea is p square contains the two-step transition probabilities. A very convenient way, two-step, very convenient way, you simply multiply p with itself, and you can do it because p is a square matrix. Contains the two-step transition probability, and similarly, that is what we mean by that is, if you look at p square of I j, this will be equal to the probability, as we already said, x n plus 2 equals S j given x n equal to S I. Okay. And similarly, extending this, you have P m, that is P times P times P performed m times, this gives the m step transition this gives the m step transition probabilities. Okay. So, I think that must be fairly clear from this derivation. In fact, something that is worth remembering, and it is very convenient once you have that one step transition probability matrix P, simply take the product m times, that is p raised to the power of m, and that gives you the m step transition probabilities. Let us look at a simple examples or a couple of simple examples to understand this. Let us go back to our industrial reliability and our stock price examples. Okay. So, let us look at simple examples to understand this. So, the first one is our industrial reliability example, right. So, we go back to our industrial reliability problem. and we have here x n belongs to state 1 comma state 2. Remember, this is your operational or this is the O, and state 2 this is your faulty or your F state, and the machine can be in one of these two states, can be operational or faulty, and it can transition from operational to faulty when it breaks down, faulty to operational when it is repaired, or it can continue from operational to operational, faulty to being faulty. Okay. So, now if you look at the one step, and we have looked at this example in detail, the one step transition probability matrix for this we have seen to be given as in our example 0.95, 0.05, 0.90, 0.10, and this naturally this is then the operational to operational, this is your operational to faulty, this is your faulty to operational, and this is faulty to faulty. Okay. So, this is the one step transition probability matrix. This is your one step transition probability matrix, and now if you compute, now if you ask what is the two step transition probability matrix, now you perform p square, that is basically p times p, which is take this matrix 0.95, 0.05, 0.9, 0.1 and multiply it by itself 0.05, 0.9, 0.1, and therefore, this gives you the two step transition probability matrix, that is 0.9475, 0.0525, 0.9450, 0.0550, and this is essentially your, now you can write that this is essentially your two step transition probability matrix. This is your two step. This is essentially your two step transition probability matrix, and so this is your two step transition probability matrix. And now if you look at this, what is this? Let us look at this. This is essentially, again it goes from O to O, operational to operational, and in two steps. And if you see how you get this, you can see to go from operational to operational in two steps, either you can go from you can go two ways. You can go to operational to faulty to being operational, or you can go from operational to continue to being operational and operational. And in fact, if you look at this product, that reflects this, right. So, this is equal to essentially the sum of these two. So, 0.95 into 0.95, which corresponds to operational to operational, that is x n to x n plus 1 is operational, and x n plus 1 to x n plus 2 is also operational. That means you have the product of the two probabilities. Remember, these are independent. So, 0.95 into 0.95, or plus you have either it is goes from operational to faulty, that is your probability 0.05, and subsequently it is repaired. So, it goes from this corresponds to your operational to faulty and subsequently repaired, and that is logical, and that you can see is essentially what you get as 0.9475, that is, it goes from operational to operational in 2 steps. Remember, it does not mean that it continues to be operational, that is the important thing. It can either have been continued, I mean it can either have continued to remain operational, or it could have broken down in the first hour and repaired in the second hour, alright. So, these are the 2 possibilities, and now you can clearly see the intermediate, the sum over the intermediate steps. There are 2 intermediate stages. Intermediate stage could have been either S1, that is continuing to be operational, or S2, where it is broken down and then repaired. Okay. And these are now your 2-step transition probabilities. And interestingly, you can see that operational to operation, that it continues to be operational, probability machine continues to be operational is 0.9475, which decreases from, that is, it decreases from 0.95. That is, originally, remember, the 1-step probability that continues to be operational is 0.95. The probability that it continues to be operational after 2 hours, now you can see is lower, it is 0.9475. So, essentially it means, and look at the probability of breakdown, probability goes from operational to breakdown in 2 steps. Operational to faulty in 2 steps, this is equal to you can see this is equal to p square of 1 2, right. This is essentially your p square of 1 2, this is 0.0525, which basically increases from the 1-step value of 0.05, right. So, originally it is 0.05, the probability it breaks down in 2 step increases to 0.0525. Therefore, now therefore, as you can see, as time increases, the probability that it continues to remain operational decreases, probability that it can break down at some point, probability it goes into breakdown increases, and that is natural, that is what you expect. As time increases, as time progresses, probability that it breaks down progressively increases. Okay. So, the probability that it breaks down, and at some point it in fact reaches an equilibrium, that is something that is interesting that we are going to see as we go forward. Thus, with time, so the summary of this, gist of this, thus with time, the probability of breakdown increases. Okay. So, that is the first example. Let us now go back and look at another example, that is our stock price example. Okay. So, let us go back, take a look at our another example, that is our stock price. And in this example, remember, the stock price can be in any of 5 states, this simple example S1, S2, S3, S4, S5, this is 100, 200, 400, 500, and the 1-step transition probability matrix, remember, if you can remember, the 1-step transition probability matrix is essentially this is your 0.8, 0.2, 0, 0, 0, 0.2, 0.6, 0.2, 0, 0, 0, 0.2, 0.6, 0.2, 0, 0, 0, 0.2, 0.60, 0, 0, 0, 0.2, and finally you have the 0.8. Okay, so this is your one step transition probability matrix. This is your one step and the two step transition probability matrix now can be obtained as p square, and you can evaluate this thing using a software such as MATLAB. This gives you 0.68, 0.28, 0.0400. Now, one thing you can still continue to observe, be it either the one step transition probability, two step or m step transition probability, sum of rows is always equal to 1. Okay, that property must always hold, okay, because whether it goes to from state I to Sj in one step or it goes from state I to Sj in two steps. Remember, the two step transition probability, three step, for all the transition probability matrices, irrespective of the number of steps, the sum of the rows must always be equal to 1, and that is the fundamental property of the matrix. Okay, that follows once again from the total probability rows, because you are taking the sum of the probabilities over all possible ending states j given an initial state I. So, that property must always hold. Okay. So, I think it is worth something interesting, and that is worth remembering. 0.28, 0.44, 0.24, 0.04, 0, then you have, I guess, 0.04, 0.24, 0.44, 0.24, 0.04, then you will have 0.0, 0.04, 0.24, 0.44, 0.28, and then you will have 0.0, 0.0, 0.04, 0.28, 0.68. This is the two step transition probability matrix, and if you look at this, so for instance, let us take this row, and then you have the sum of the probabilities 0.04, 0.24, 0.44, 0.24, 0.040, that is 2. So, sum of all the probabilities. So, you see sum of probabilities in each row equal to always holds for any transition probability matrix, always holds. This is a fundamental property. This is fundamental property which always holds. Okay, it would serve you well to remember that this is a fundamental property which always holds. And now, if you look at, for instance, this, let us take a simple, this is essentially P35. That is, we are asking what is the probability xn plus 2 equals 500 that is state 5 given xn equal to state 3 that is 300. The way this can occur is if it goes from 300 to 400 and from 400 to 500. This is the only possible transition, because from 300 it cannot directly go to 500 and no other transition is possible. And 300 to 400, remember the probability, each of these probabilities is 0.2. So, this probability by independence is again 0.2 into 0.2 equals 0.04, and that is how you get this entry. This is essentially your 0.04, and similarly that can explain also all the other entries. I mean, you can also finally deduce how you can get essentially from, for instance, let us say you know, something like I mean, you can reduce the rest of the probabilities in a similar fashion in this transition probability matrix. So, the summary of this is essentially very simple, that if you have the transition probability matrix, as I have already told you before and we already seen before, that completely characterizes the DTMC, discrete time Markov chain. And now you also seen an implication of that. Now, the one step transition probability is P, two step transition probabilities are given by P square, m step transition probabilities are given by P raised to the power of m, that is P, the matrix P multiplied by itself m times, and in particular if you look at any row of this matrix, any P m, all the rows have to add up to unity. That is a fundamental property. Alright, so after this interesting module, let us take a break here and we will continue with other interesting aspects of DTMC analysis, that is discrete time Markov chain analysis, in the next module. Thank you very much.